For centuries, sailors spoke of walls of water appearing from nowhere, swallowing ships whole. Science dismissed it as folklore, just unusually large waves, a statistical fluke in a storm. But the truth is far stranger. In January 1995, a laser sensor on the Draupner platform in the North Sea recorded a 6-meter wave, taller than an 8-story building. It was the first scientific proof that rogue waves exist. But here's the twist. Rogue waves are not random. They arise from non-linear focusing, where waves steal energy from each other, creating monsters that defy probability. Science still struggles to predict them. A rogue wave is defined as a wave at least twice the height of the surrounding sea state. In practice, that means a wall of water over 30 meters tall, the height of a 10-story building, appearing without warning. For centuries, such waves were dismissed as sailor folklore. Then, on January 1, 1995, a laser sensor on the Draupner platform in the North Sea recorded a wave of 6 meters, the first scientific measurement of a rogue wave. It was no myth. This measurement changed everything. It proved that rogue waves are real and far more common than models predicted. Unlike tsunamis, which are caused by underwater earthquakes, these waves can form from nothing, a sudden, violent collision of ocean energy. On January 1, 1995, a laser sensor on the Draupner platform in the North Sea recorded a wave 6 meters tall, the height of an 8-story building. This measurement was the first hard proof that rogue waves exist, transforming sailor folklore into scientific fact. So, why did this measurement change everything? Before Draupner, rogue waves were thought to be statistical impossibilities. The ocean's random waves should never combine to such heights. But here, the wave was over twice the significant wave height, the standard measure of sea state. That single laser pulse shattered decades of skepticism. One crew member recalled, "The wave came from nowhere. It was at least 25 meters high. We were lucky to survive." Suddenly, rogue waves were no longer myth. They were a measurable, deadly reality. What happens when a rogue wave strikes a ship? In 1978, the cargo ship MS München vanished in the North Atlantic, leaving only scattered debris. A German maritime court later ruled that a rogue wave was the likely cause. A silent, invisible executioner. 2 years later, the MV Derbyshire vanished in a typhoon near Japan, becoming the largest British ship ever lost at sea. A survivor recalled, "We saw a wall of water coming at us. It was like a mountain. The ship just disappeared." Over 200 ships have met similar fates in just 2 decades. Even modern ships are not safe. In 2019, a monster wave struck the cruise ship Viking Sky in the Norwegian Sea, injuring several passengers and forcing an evacuation. The wave appeared without warning, proving that despite our technology, the ocean still holds deadly surprises. So how does a wave steal energy from its neighbors? The answer lies in non-linear focusing. Imagine 2 waves traveling at slightly different speeds. As they meet, they can merge, concentrating their energy into a single, towering wall of water. This is fundamentally different from constructive interference, where waves simply add up. In non-linear focusing, the waves actually distort and steal energy from each other, creating heights that defy linear models. The ocean is far more chaotic than our equations predict. And that chaos is why rogue waves remain so hard to predict. The same non-linear equations that create them also make them nearly impossible to forecast. The sea is not a random machine. It is a non-linear beast, and we are still learning its language. In 2004, satellite data revealed 10 waves over 25 meters in just 3 weeks. The probability of such a wave in any sea state is estimated at 1 in 10,000 to 1 in 100,000. That's rare, but not impossible. The problem is that our models still can't predict when or where a giant wave will strike. Non-linear focusing, where waves distort and concentrate energy, is chaotic and sensitive to tiny changes. Even with better data, forecasting remains a gamble. Modern ships are designed to withstand waves up to 15 meters. But rogue waves can exceed 30 meters, twice that threshold. A ship built for the expected can't survive the unexpected. So, where does this leave us? Despite decades of data and billions in research, rogue waves still defy prediction. Dr. Johannes Gemrich of the University of Victoria puts it bluntly, "We have measured waves over 30 meters. That is the height of a 10-story building, and they can appear in minutes. Our models tell us such waves should occur once in 10,000 years, yet satellite data shows they happen far more often. The ocean is not following the rules we wrote for it. The mystery is humbling. We have mapped the genome, split the atom, and sent probes to Mars, but the sea keeps its secrets. Rogue waves remind us that nature still holds cards we haven't learned to read. But where does the energy come from? Rogue waves often form when strong currents, like the Agulhas current off South Africa, oppose incoming swell. The current squeezes and steepens waves, concentrating energy into a single towering peak. Some rogue waves come in groups. Mariners speak of the three sisters, 3 giant waves in quick succession. The first disables the ship, the second floods it, and the third sinks it. This pattern has been observed in several disasters. Rogue waves aren't limited to storms. In 1942, the Queen Mary was struck by a 28-meter wave in calm weather, nearly capsizing. Such freak waves can appear even in moderate seas, catching crews completely off guard. Satellite radar altimeters have since scanned the global ocean. Analysis of 2 billion wave measurements showed that rogue waves occur far more often than chance predicts, about once every 2 days somewhere in the world. The Draupner wave was not just tall, it was steep. Its front face was nearly vertical, like a moving wall. That steepness is what makes rogue waves so destructive. They hit with the force of a solid object, not a fluid. Most rogue wave measurements come from the Norwegian Sea and Atlantic, but the Southern Ocean, with its fierce circumpolar currents, likely breeds even larger waves. We simply lack data there, a blind spot in our understanding. Researchers are now using machine learning to predict rogue waves. By training neural networks on decades of buoy data, they can identify precursor patterns, subtle changes in wave shape that precede a monster wave. Ship designers are also adapting. New hull shapes and advanced materials aim to withstand the unexpected. But no ship can be built to survive every rogue wave. The ocean's power is simply too vast. But where does the energy come from? Rogue waves often form when strong currents, like the Agulhas current off South Africa, oppose incoming swell. The current squeezes and steepens waves, concentrating energy into a single towering peak. Some rogue waves come in groups. Mariners speak of the 3 sisters, 3 giant waves in quick succession. The first disables the ship, the second floods it, and the third sinks it. This pattern has been observed in several disasters. Rogue waves aren't limited to storms. In 1942, the Queen Mary was struck by a 28-meter wave in calm weather, nearly capsizing. Such freak waves can appear even in moderate seas, catching crews completely off guard. Satellite radar altimeters have since scanned the global ocean. Analysis of 2 billion wave measurements showed that these extreme waves occur far more often than chance predicts, about once every 2 days somewhere in the world. And that is why we keep exploring. The ocean's final mystery is a call to curiosity. If you want to join us on this journey, subscribe and never miss a story, because the next wave might just rewrite everything we know.